All right.
Okay.
Hello, everyone. Welcome to the Northeastern Large Language Model System Seminar. So today it's our pleasure to have Yunchi here. So Yunchi is a PhD student in computer science at University of Michigan. His advisor is Ryan Huang, and his research interest lies broadly in developing principled technique to improve the correctness, observability, and reliability of large-scale systems. Recently, as you can see from this piece of work, he mostly focused on addressing silent bugs in various components of machine learning systems. With that, take it away.
Okay. Hi, happy Halloween. I'm honored to introduce our research work, TrainVerify, equivalence-based verification for distributed LLM training from University of Michigan, Microsoft Research Asia, and jointly done with your great Professor Tan. So, training production scale language models require huge computation and memory resources, which makes the distributed training a must. The success of scaling law has triggered an arms race for increasingly large models, and their training is extremely costly. As the table shows, the latest models, for instance, are trained on thousands of high-end GPUs for several weeks or months, costing millions of dollars. Yet, the distributed training is extremely complex. It spans the entire software and hardware stack. To name a few layers, it contains model code and parallelization, orchestration, and graph optimization to low-level GPU kernels, all while supporting diverse hardware platforms. And each layer adds to the complexity, so together they have more than millions of lines of code. This makes the distributed training extremely error-prone. So from various types of faults, we identify one major class of bugs that is most elusive and costly, the parallelization bugs, which only surface at the distributed settings, such as the wrong tensor partitioning, the misused communication collectives, or faulty pipeline scheduling. Such bugs directly jeopardize the correctness of distributed training, and even worse, many of them are silent. They don't crash the training, but can evade detection for weeks. And by the time of problem surfaces, the model has already burned through millions of GPU hours, wasting huge amounts of money, energy, and human effort. For example, there was a Magtron bug involving the incorrect loss scaling in the context parallel logic. The root cause was simple. There was a wrong scaling factor among multiple rounds of tensor synchronization, and it took developers and users over 10 days to fix it. While the most challenging part was to discover the bug, when we looked into the commit history, we found it had actually been introduced 8 months before it was being noticed. So very likely many models are trained without anyone realizing it. And we want to emphasize it is not just a corner case or unique to a specific system. We did a comprehensive bug study across three SOTA training frameworks and found they all encounter such parallelization bugs in nearly every aspect of their workflow. So, given a high stake, we wonder, can we formally verify that the parallelization logic is correct before distributed training starts? This goal needs to be grounded in the reality that the parallel training systems have a complex technology stack with tools from diverse vendors that evolve and update rapidly. So it is impractical to verify an end-to-end training or to rewrite a correct by construction system, which would require prohibitive effort. Therefore, we also aim for the practicality. We want to support existing systems and keep verification effort moderate. Luckily, we observe that some principled parallelization frameworks have a well-defined representation called execution plan. It is typically structured as a data flow graph where nodes are DNN operators and edges are tensors, and they are assigned to concrete devices, the GPU ranks. And the execution plan is effectively an instantiated parallel graph that is transformed from the single device model. So it captures the parallelization logic. And once an execution plan is fixed, it is used for driving the training through simple code emission process. So our key insight is that parallelization bugs are well contained, and the correctness can be reasoned about at the level of execution plans. In contrast to the source code, this representation is cleaner and more structured, so it provides an opportunity for tractable verification. Based on these insights, we propose an execution plan-based approach to symbolically verify the parallelization correctness. As the contribution of our work, we introduce verifiability into the complex LLM training system, and we built a tool called TrainVerify that makes this approach practical and scalable. Well, as a trade-off, TrainVerify maintains a focused scope to keep the verification tractable. Specifically, we target the correctness of parallelization logic and do not cover other classes of bugs, such as low-level memory buffer management or GPU kernel implementation errors that you have a bug in your CUDA programming. So essentially, parallelization is to transform the logical model, which assumes a single device execution, to a parallel execution plan by partitioning the tensors and operations, assigning them to the GPU ranks, synchronizing the distributed states through the communication, and scheduling them in the correct execution order. Then, a buggy parallelization may partition the tensor using wrong slices or wrongly transform the operators, especially when they have rank-dependent arguments, such as number of local heads in the self-attention, or they can miscount the number of replicas of a tensor, causing wrong scaling of the tensors and metrics. And when synchronizing the states, there can be wrong communication primitives being missed or added, or they are invoked on wrong groups of GPUs for communication. So these parallelization bugs cause the parallel execution plan to diverge from the logical definition of the model and leading to the incorrect model updates. Therefore, checking the equivalence between the parallel execution plan and its logical model is essential for eliminating the parallelization bugs. Formally, for any input X, the dual graphs should produce the equivalent outputs. And we want to check the equivalence symbolically in order to eliminate the numerical noise. Deep learning relies on the float point computation, which naturally introduces a numerical drift. And this compromise value-based equivalence comparison. Specifically, the conventional differential testing can report false alarms even when the parallelization logic is correct. For example, on the CPU, you can run this Python code by yourself. You simply want to add three float point numbers, but depending on whether you start by adding the first two numbers or you start by adding the later two numbers, it will give you different results. And in differential testing, the different results means they are not equivalent, although they are algebraically equivalent. Or on the GPU, you can run the matrix multiplication, but you only want the first row of its final result. You can do it by slicing out the first row of the A and do the matrix multiplication with B, or you do the MN between A and B, but you slice the first row after this operation, and their results can differ very significantly, although their transformation is actually mathematically equivalent. So these are the numerical noise, and the parallel training has many factors that further amplify these numerical drifts, such as the parallelization, the difference in the kernel implementations, and the use of mixed precision training. So we want to verify the equivalence symbolically. And given this goal to symbolically verify the parallelization equivalence for execution plans, here comes two major challenges. What is the representation to carry out the equivalence checking, and how to scale the verification to large deep neural networks that have hundreds of billions of parameters? As their execution plans can be very large, it can contain millions of nodes and operators. So as a brief overview of TrainVerify, we propose a symbolic data flow graph and lineage to carry out the verification and achieve scalability through staged parallel and shape reduction designs, which mitigates two major sources of complexity. Symbolic data flow graphs are constructed on top of the execution plans They preserve exactly the same structure as the original graphs, while adapting tensors and operators into the symbolic form. While one could use a single symbol to represent an entire tensor, we actually found it difficult to reason about the equivalence at the pure tensor level because tensor algebraic properties are too diverse across deep neural network operators and the parallel strategies. So, TrainVerify takes an alternative approach. Symbolic tensors are modeled as multidimensional arrays with symbolic elements in it. And operators are rewritten to conform to the PyTorch operator definitions. So passing the symbolic tensors through these graphs, we can obtain the algebraic expressions for the final model outputs, on which we can perform the equivalence checking. And as a bridge between the dual graphs, the lineage is a crucial data structure that encodes the tensor mapping and the partition semantics. It specifies how a subtensor is sliced from its logical full tensor and whether the additional value aggregation is required for reconstruction. For example, the tensor C, it is a lower half of the tensor A, while its value is not partitioned. And the tensor D, it has exactly the same shape as the tensor D, but it is also value-wise partitioned, so need to be aggregated with someone else. So similar concept of this lineage, the tensor mapping exists in multiple systems such as the B tensor, P tensor, which stands for the virtual tensor, physical tensor in Scalar, and the D tensor in the PyTorch. So with the tensor IDs following the SSA convention, we can easily align these related subtensors to their parent tensor, the full tensors, and convert the lineage into the expressions, such as the A is equivalent to the concatenation of B and C on its axis 0, or D is equals to E plus F. And these expressions serve as the concrete specification of parallelization equivalence that we are checking. And one of our scalability technique is the stage decomposition guided by the lineage, which addresses the complexity of extremely deep DNN architecture, where the output expressions can be very lengthy and nested, which causes intractable complexity for the solver that can report unknown or out of memory. So this decomposition is guided by the tensor lineage and break down the end-to-end verification into smaller tractable stages. So in practice, the algorithm is simply do the repeated backward sliding on the dual graphs. It starts by traversing the logical graph, the single device graph, because we view it as the reference implementation. We traverse it in the execution order, and we assume we already have some stages already cut it. So whenever we have a new unvisited lineage, in this case it's BEF, we start to form a new stage, and this unvisited lineage will serve as the output boundary of the stage. And we do the backward tracing on the dual graphs until we meet some already verified lineage, in this case ACD, and we repeat this for all inputs. And in this simple example, we only have this one dependent input, so we are good. And it serves as the input boundaries. So once we have the input and output boundaries, we can slice out these two subgraphs and it forms a stage. And we continue, for example, for BGH, and also slice out a new stage. And this new stage for the logical graph, it just that do nothing. It's just simply identity. While in the parallel graph, you may slice out a few bunch of communication operators, etc. So we keep this going and get a series of stages. Then verifying a single stage is like this because each stage carries the lineage for its input and output tensors as boundaries. So verifying the equivalence of a single stage is to check that the output equivalence is always true given the input equivalence and the operations within the stage. In this example, we check D equals to E plus F is always true given this A is sharded into B and C and these operations in the middle. So all stages can be verified independently and executed in parallel while being chained together to form an end-to-end equivalence proof. And also a failed stage then indicates a localized equivalence violation, and equivalence checkers will also produce concrete values for tensors to facilitate the diagnosis and debugging. Since tensors now have symbolic real as elements, keeping their full original tensor shape, sometimes with millions of elements, introduce significant complexity that the solver cannot handle. So shape reduction mitigate this by leveraging the repetitive nature of the operators, where the same operation is applied repeatedly across the multiple subtensors. So if you look at this basic matrix point multiplication and these two elements C11 and CT2 or other elements, they actually have very similar this pattern. Their operand are the same while their inputs are subtensors that are shifted in the index. So to reduce such redundancy, we perform the verification on symbolic data flow graphs with only tensor shapes reduced. We ensure that the shape reduction preserve the original structure and functional properties by following a few types of constraints so that the verified equivalence on the shape reduced models faithfully extends to the original full scale models. And these constraints looks like this. We have shape alignment constraints, which starts by initializing each dimension to have a initial range. In this case, is each dimension should be at least one and smaller than its original size. And the shape alignment constraints enforce that the shared dimensions keep consistent across multiple tensors. So in this matrix multiplication examples, these two input tensors, they should keep the same k dimension and they propagate equivalence of m dimension and n dimension to its output c, etc. And if this operator is a reshape, then these constraints will express that the total volume is still kept before the same before and after the operation. And the semantic intactness constraints aims to preserve all the operations at small scale. So for the matrix multiplication, this is its formula. So it basically will enforce that you have the k dimension for this operator, his k dimensions will be at least two. So it will not lose the add operation. And we not only collect this operator's constraints, we actually collect all the operators constraints from both this logical graph and the parallelized version. And we also enforce the lineage relations between the tensors that are sharded or replicated or value-wise partitioned, etc. So under all these constraints, we minimize the total tensor volume and get a shape-reduced models that we perform verification on. And TrainVerify designs a modular graph and the solver interface for more convenient adoption or extension. The implementation leverages Nscaler as graph backend. So Nscaler is a compiler-based parallelization framework which includes an augmented graph tracer and provides IR graph, intermediate representation graph, for the parallelized models. So we export its vtensor, ptensor metadata for our lineage construction. So the lineage is automatically generated instead of hard-coded or empirically set by human. Well, so you might have a question whether these lineage could go wrong in the sense that they being consistent with the actual parallelization and what will happen if it is wrong? Can they cheat our verification? So the answer is we can normally trust this lineage is correct, while if we are unlucky that the lineage has some mistake, the verification still has some guarantee. It is guaranteed that there's no false pass because in each stage its input lineage is guaranteed to be verified by its prior stage or it is initialized. And of course, the initialized stage goes through some sanity checks to make sure it is correct. And the output lineage is verified by executing the stage. So when all stages pass, the equivalence is guaranteed for this end-to-end equivalence. And there's no way that verification can be cheated by the wrong lineage and we are safe. But it is possible to have a false alarm in case there is wrong lineage that inconsistent with the actual model. It will fail the stage because the checker will report that this lineage may not always hold. It is not consistent with the model. So no matter whether the actual parallelization, the model is correct or not, the verification will not pass. And if the model is actually correct, then this is a false alarm. But if the model is wrong and it is a true alarm. So in practice, we normally trust this lineage is reliable, so we won't get into too much trouble of the false alarms. And we use the Z3 for equivalence checking and rewriting those reusable symbolic operators. Particularly, we designed a hybrid equivalence checker, which first performs efficient expression comparison. So if it shows two expressions are equal, then we are good. This process is sound. So if it reports this to zero, then they are the same. This process is efficient but very superficial, meaning it can has false alarm if the two expressions they are mathematically same but they are very different in shapes, the checker may view them as different. So so whenever the expression this checking fails, we fall back to the SMT solver, which is much slower but is sound and complete and can produce concrete tensor values for the equivalence violations. It will like produce a solution to the satisfiable non-equivalence. And as shown in these examples, the effort of operator rewriting is actually moderate due to the Pythonic syntax of the Z3 and NumPy, and their correctness, the correctness of these rewritten operators is easy to reason about and thus guaranteed. The TrainVerify has supported symbolic operators for the general LLMs, and they can be reused whenever used for verifying other models variants. The adaptation is only needed when you introduce new operators or you have some custom operators. Yeah. So we evaluate TrainVerify on the Llama 3 and DeepSeek V3 models. The verification runs on a single machine with a 32 core CPU and 1.3 terabyte of memory. For the largest model variants with hundreds of billion parameters, parallelized across 8,000 GPUs, the verification successfully complete within up to 9 hours. The cost is acceptable compared with the weeks or months of training, and also the verification can run asynchronously alongside the training without blocking the production workflow. And our scalability trends show that the shape reduction is effective, so the verification cost is invariant to the original tensor flows, tensor shapes, such as the global batch size, the hidden dimension, or the sequence length. And the verification cost is linear to the number of model layers and the parallelization degrees, such as data parallelism and tensor parallelism, because the size of the execution plan grow linearly with respect to these parameters. And we also test our implementation via bug reproduction. We reproduced 14 representative cases selected from our bug study, and it shows TrainVerify is able to eliminate the broad categories of parallelization bugs, such as the incorrect communication, where you might miss and or reduce when you do the tensor partitioning, or you set the wrong communication sources or destination ranks. You might incorrectly partition the tensors and operators by splitting a non-partitionable dimension, or you wrongly scale the rank-dependent argument, and also miscount the tensor replicas, so you have wrong scaling or norm calculations. And in our own use experience, it also uncovers new buggy parallelization, such as sharding these non-partitionable dimensions in the Llama models, or it discovers some broken data dependencies and the violation of SSA conventions in those execution plans. And in the end, I would also like to briefly discuss a direction of future work. One assumption of TrainVerify is it requires the training framework can provide this data flow graph representation and the lineage information. So this is normally compatible with the compiler-based parallelization frameworks such as Nscale or APA because they internally convert the original source code model into graphs and do everything on the graph. While in the meantime, there is also a body of tools such as Megatron or DeepSpeed that embed their parallelization logic directly in the PyTorch and Python code. So this is what we call eager mode. And they are not graph-based, but they are actually the dominant workhorse in the industrial production. So a potential approach to extend such framework um, is, is to leverage some tracing tools such as Torch Dynamo to get their graph on which we can do the verification. But it is not easy because the graph capturing from the Python code actually requires much effort, and even the state-of-the-art tracing tools are not perfect, and they have many limitations. Right. While recently, we are delighted to see that the machine learning community is actually embracing the trend of more principled AI infra. In the latest PyTorch conference 2025, which is just held 1 week ago, there were many attention and focus on these compiler-based parallelization and graph capturing things. This not only facilitates the potential adoption of TrainVerify, but also provides a lot of opportunity in enhancing the reliability and correctness for the messy ML training, of course, and inference. So, as a summary, we present TrainVerify. It targets the correctness for parallel training and focus on model parallelization. It symbolically verifies the parallelization equivalence at the level of execution plans, and designed a bunch of representation and scalable techniques. It is now open source at GitHub. Thanks for listening.